Welcome to Calculus.
We overcomplicate even the simplest task.
On this episode, Stevenson will demonstrate
Here's another related rates problem. Take a moment and write it down. Be very careful to get the correct numbers when you do this problem. As I read it, I'm going to annotate key words or phrases or their values. Here we go. Okay, lots of information here. Let's start by trying to make sense of this with a picture. So we have some police cruiser approaching from the north. All right, so let's remember, never eat soggy waffles. So the police cruiser must be up here, but then the speeding car is headed east, so it's over here. So we can see we're going to create a right angle, because that's the intersection, right angled intersection. So it's going to look something like this. So here's the police car, and then here is the speeding car right there. And then there's the right angle intersection. Okay. When the cruiser is some distance from the intersection, so we'll call that Y, the speeding car is another distance east of it. So let's call that X. Just because vertical is usually Y, horizontal is usually X. But what it tells us is that they also says the distance between them is a certain rate. So that means they're measuring this distance between them right there. Let's call that Z. So they're measuring the distance between them as they are being referenced from this point of intersection. We have references at certain points, but what we need to do here is we need to create an equation. There's nothing given to us here. So we need to first create an equation that relates these three measurements here. Well, hopefully you recognize if we're using all three sides of a triangle, we can use Pythagorean theorem. Pythagorean theorem is going to help us work with fixed values. The problem, though, is that we have two objects moving simultaneously. So we need to differentiate this so we can create a related rates equation. So we're going to differentiate this with respect to time on both sides. And we're going to use implicit differentiation to do that. Now that we have our related rates equation, what I suggest you do is make a list to the side of all of the differential expressions, so like dx dt, dy dt, dz dt, and any additional variables like we did in the previous example. Now that I have my list, what I'm going to do is refer back to my problem and see what I can fill in here. Now, x, y, and z refer to the fixed distances at those spots there. But dx dt, dy dt, dz dt is referring to how that distance is changing over time. So we need to be careful when we read this. So let's start right about here. It says when the cruiser is 0.6 miles north of the intersection. Okay, so that's going to be the y value. Let's see, and the car is 0.8 miles to the east. Okay, so that's going to be this distance x. The police determined with radar that the distance between them, so that's z, is increasing. Okay, that means it's changing at 20 miles an hour. That is a rate. So we're not going to put 20 into z, it's going to go into dz dt. Again, how did I know that? Because it said 20 miles per hour. It's a rate of change. If it just said a number and it just said a distance of miles and not miles per hour, then it would have gone into Z. If the cruiser is moving at a speed of 60 miles per hour, all right, so the Y is the distance of the police cruiser to the intersection. So if it's talking about its rate of change, that's going to be dy dt. Then what is the speed of the car? Well, the car's distance from the intersection is represented by x. So if it's asking for speed, that must be distance over time. So we need the rate of change of x. So that's going to be dx dt. So that's what is it asking. So there's our question mark. That's our unknown. Now let's look back at our list. Do we have everything we need? Well, not really. Look at z. Z's unknown. So we have a problem. So we need to go back at our picture and see if there's a way we can figure out what z is. Well, look at the relationship. We know it's Pythagorean theorem. You see that? So what we can do is plug in x and y into our Pythagorean theorem and use it to solve for z. So I'm going to go off to the side here and do that. Now we have all the values we need. So we're going to take all these numbers that we have and we're going to plug it into our equation here, and then we're going to solve it for dx dt. Now, according to this, my answer is dx dt, I got negative 20. Now, this would mean that the speed of the car is 20 miles an hour, but since it's negative, that means it would be headed towards the direction of the intersection, because negative would be left. So I'm guessing I made a sign error. So let me go back and check my setup here. So this is increasing, so that was positive. These distances were positive. I bet I made a mistake with my dy dt. Let me look. 60, 60. So it said that the cruiser was moving at the instant. Wait, the car is increasing as the distance. Oh, as it's moving towards. Oh, that's right. The cruiser is moving towards the intersection. That means that distance is decreasing. So we should make 60 negative. So how does that? So let's go back in here. So that's negative. That's negative. That should be negative. So we're going to add that. So then that's going to be 1112. And then that's going to be positive 70. Now that makes a lot more sense. The speeding car is moving away from the intersection. So if you think of this as like your origin, if you move to the right, the direction, that vector would be positive, okay? The police cruiser is moving towards the intersection, so that would be in a down direction. The vector is down, so it makes sense that its dy dt was negative. So let's answer the actual question now.